Hey again, everyone. Thanks for joining. I see we've got a pretty good audience today, so thank you everyone for taking the time, especially as we're leading up to or into the holidays already. Um, I do think we'll have a pretty quick presentation for you here today, and uh, go over some of the new items, some of the changes in Signal Pro, and also refer you to a document where you can get some more information. And I've also got the sort of what I think of as the three top new features that might speed things up and make life a little bit easier for you. Um, Unfortunately, I don't have Rory or Kevin this morning to sort of take a look at the question and answer field and handle that side of things for me. So if you do have any questions as I'm going along, please do feel free to use the chat window or oh oh, I see. Oh, okay, somebody has raised their hand. Let me Peter, I see you've raised your hand. I'm going to go ahead and hit this allow to talk. Did you have a question?
Sorry, no, that must have been an accident. I didn't intend to.
Okay. Well, hey, it was a great test of the feature anyway, so I'll go ahead and put you back on mute here. Um and oh, it looks like Ronald, have you got a question for us or also just discovering the button?
Okay, yes, I do. The chat is currently disabled, and would you be sharing the slides and the recording?
Yeah, we will have a recording after this is all done, and I've also got another kind of much more comprehensive document to point you to in the slides. So I guess thanks for the heads up. The chat's not working. I wasn't aware of that. We'll just use the raise hands feature, and I'll try and stop and leave some room for questions at the end as well. I think most of what we'll be talking about, especially I see some of you on here today that have already been to some of the previous webinars on this topic, and it's been sort of an evolving topic. So there will be a little bit of new information today, but probably much of it will be review. So I'll go ahead and jump into this. Again, we're looking at land mobile, LMR, or DMR planning, and particularly some of the study updates for for 2025 or what we've kind of done in the last year or two as we've evolved and updated some of these studies. So jumping into the first big sort of category of changes and really what this meeting's all about um, is the category of studies called the TSB 88 studies. And those are only really for looking at the downlink case and specifically in a simulcast system or a system that has some simulcast in it. So if you're not doing simulcast planning, if you're doing multicast planning or something like that, then these changes don't really apply to you. But you might want to take a look at the document anyway. And the document I'll be referring to is actually not the slides today, but it is this. If you go on to the support portal on EDX, there's an article here called Simulcast Planning with the TSB 88 Monte Carlo Studies. And if you just do a search for simulcast or TSB 88, this should pop up for you. Um, I've also got that link here in the slides, the direct link to this. I was going to try and put that in the chat. Maybe I'll just try anyway. Maybe you're not allowed to write in the chat, but I am. So let me try this real quick. Um, but again, if you just go onto the support portal under the knowledge base category, you'll be able to get to this article, which gives some guidelines and refers to the document that we're talking about and so on. But the part of this sort of how-to or tutorial document, we give some definitions about the problem of simulcast delay spread and what the vocabulary are that we're sort of talking about here. Um, and of course, describing the simulcast performance curve or the delay versus signal file here. And I'll dive into kind of the basics of what the study does here in a minute when I jump to SignalPro. Um, but if this stuff is unfamiliar to you, definitely do go through this document if you're looking at doing simulcast planning and sort of read up on what the recommendation is, read up on some suggestions about how to set up your propagation model here. And in this, the main consideration is talking about setting up your propagation model to try and predict the average or the mean signal level that you would find out in the field versus setting up the propagation model to be deliberately conservative to show sort of a worst case um, propagation. And we could call that a faded propagation model versus maybe an unfaded or an average propagation model. And it's important that you know sort of which way that you're accounting for fading, whether you're using a fading study or a faded propagation model. And that goes into here, or goes into sort of some detail on that. But really, the section that's got an update and the information in this document that's going to be new to you, even if you've been using SignalPro to do LMR planning for years, is this section here that defines all of these different study types. And here I'll go ahead and jump over to an example project that I have set up that shows a bunch of these different simulcast study types. And the one that we're looking at here is our TSB88 Hess simulcast Monte Carlo reliability. And this is the sort of full boat simulation of delay spread and fading to come up with a reliability at each grid cell. So in this kind of super flat earth, super simplified example, what I've done is put two simulcast cells or sites here with equal amounts of delay so that basically this green stripe that you see here of high reliability in the 99% here is where the delay spread is sufficiently low between the two sites that there's no possibility of time delay interference. So essentially, those signals are reinforcing each other, and the coverage is at an even greater reliability than it would be with just one of those sites. And then suddenly there's this hard edge transition. And this is something that folks have asked about when looking at these studies. You'll see something very similar in the aggregate reliability study and et cetera. And what this represents is the transition point where, for example, on the left hand or the western side here, this is the transition point where my western site is the strongest or the signal that the mobile is locking onto, but the signal coming from my eastern site has now exceeded the allowable delay spread. And so any of its signal power is serving to distort and interfere with the strongest server. So this transition is really about the reliability with time delay interference accounted for. And what could potentially happen here is when you cross into this space, you're at a greater risk of getting, audio problems as a result of sometimes potentially momentary time delay interference. It does not necessarily mean that you won't have coverage in this area, but it means that our reliability calculation is showing a much degraded reliability because of delay spread. And of course, the fact that I've put these sites at kind of the perfect distance to get bad delay spread between them, you would never build this sort of a thing in the real world. And we would have terrain and clutter to sort of isolate the signals from each other. But I did this sort of pure example as a way of comparing the different study results and of showing you at its simplest what these new version 2 studies are doing compared to the version 1. And so that's essentially it for each grid cell, and there's a few different flavors of this reliability study, but for each grid cell, we're finding the average signal level according to our propagation model settings, and finding that average signal level from each of the sites involved, letting those signal levels fade up and down over time, and also calculating the Hess delay spread so that we can sort whether a given secondary or third signal coming in is potentially interfering, potentially a source of time delay interference, or uh, potentially constructive. And really, that's one of the important changes that we'll look at. I'll switch back to the slides here in a moment. But in the very first revision of some of the studies, that sorting had been essentially simplified so that you would not always see the area where there's no possibility of time delay interference. You would not necessarily see that improvement in reliability. Um, so let me switch back to these studies and or the description of the studies here and get my slides back. And I'd like to talk about the difference between those original studies, and you'll see in the list here there have been in the software for years now. We've had our Hess Simulcast Monte Carlo reliability. We've had our bounded area Monte Carlo bounded area coverage and our aggregate reliability. And now suddenly we've got a new version 2 of all of those studies. So the main question I want to answer today is, well, what's the difference? What changed in those studies, and why did we leave the originals in place? Um, so essentially, EDX originally worked with Bernie Olson of the TSB 88 committee. Our development team and Bernie worked together to come up with a proof of concept for this Monte Carlo method, and that's what got deployed in the software. You know, the original version 1 of these studies were those original studies as Ted and Bernie had sort of agreed on and were happy with when they were first released. Um, in recent years, we've made a few adjustments and updates to them. One to address a feature request, which I'll get to in a few, but also because when we went back and looked at the TSB 88 documentation, we found that there were a couple differences in how it was written in the document versus how we had originally implemented it. And I see that Peter's got um, a question. Are you raising your hand, Peter? I think I have allowed you to talk. Oh, I see. There's a Q&A panel in here.
I was raising my hand. I have not knowingly done anything.
Oh, okay. Sorry about that. Don't mean to put you on the spot. I see one question in the Q&A section. Yeah. The question is essentially the version 1 study versus the version 2. And it seems like the version 2 uses the required simulcast delay parameter. And this is sort of what I'm addressing. So I'll jump back in here. So in the sorry, I got a little distracted by the appearance of questions. Um, so in the version one of the studies, these are some that we had gone back and forth with and tested and implemented. And yeah, there are a couple of differences. The version one studies and a couple differences may have been more simplified in their sorting. And Julian, that's the difference, the key difference that you're seeing there in the version one of the study. It the the study is using the faded signal levels and a fixed sort of static RMS delay value, which wasn't quite how the standard ultimately was written, and it didn't wasn't quite in keeping with sort of the original concept as our team had understood it. Um, so in the version two of the studies, there are really three key differences that you'll find between the version one and version two. The first one is probably the most subtle. We discovered that the fading calculation, which is used to approximate sort of how much signal fading you get over time and what that distribution looks like, our fading calculation did not match the one proposed in the written released version of the spec. Our distribution wound up being a little bit more narrow in terms of signal powers, in terms of how the two distributions overlay with each other. And so we went ahead and updated that so that our fading calculation is in line with what the NTIA has recommended for doing these fading predictions. The second one, like I said, this is the one that you're really going to see a difference with. In the version two of the study, whether we're talking about the Hess reliability or we're talking about the aggregate reliability, um, or however, whichever of those version two studies you're looking at, we're not using the static RMS delay spread value as calculated based on a static signal prediction. Instead, what we're doing is looking at the delay time of any potential interferers at each Monte Carlo draw. And if that delay time is within the allowable delay spread window of the strongest signal, then we do not count that as an interferer. It's potentially constructive interference, but we're actually not adding any gain there either. We're just saying, okay, this is not interfering or not generating any possibility of TDI. Whereas as soon as, again, jumping back to my screenshot here, as soon as the distance between the two sites hits the right distance for that delay value to be inside or outside the allowable time delay window, then that signal power will count as interference and it will effectively degrade the signal to noise ratio that we're using to try and reach the channel performance criteria. And again, that's why you see this hard edge here. Um, and again, you will see if you have run the version one studies in the past, with the aggregate reliability, it's pretty darn similar. But some of the other studies, especially like the bounded coverage, you may get very different results. And so, the natural question is, well, which one is right? And I'm not sure there really is an answer to that question. They're just slightly different methods of simulating this and looking at the potential for TDI. Our recommendation is to use the Hess Simulcast Monte Carlo Reliability version 2. And that's assuming you can provide that simulcast delay versus signal file. And so jumping back to my how-to document here, that would be this table. If you can provide the table of the allowable delay spread for a given signal to noise ratio, then that's sort of the most detailed simulation we can do. And the aggregate reliability study, I'll jump back to my SignalPro window here. If I go into my TSB88 studies setup, the aggregate reliability study is not going to use this simulcast curve file. It's just only going to use oh, sorry, it's not going to use this field. It's just going to use the required simulcast delay time. And again, this is the delay time where inside of that window, it's allowable delay spread, and outside of that window, it becomes interference. And we can also put a requirement for CPC. Um, and then down here is how many in running the Monte Carlo, how many samples we're going to get per grid cell and how much fading we want to account for. And so, especially in maybe a dense urban environment or high fading type environments, you might increase that number. Um, but so the aggregate study is going to just use those values instead of the simulcast curve, whereas the simulcast curve uses or I'm sorry, whereas the Hess version of the study uses that simulcast curve to describe the performance of the receiver. And in the Monte Carlo, it's testing against that table at each trial. And that gives you, again, more sort of detailed results. Um, I do want to show you this though, because I've got the Hess version reliability set up here with a table that's very much in agreement with the values I used for my aggregate. And if I switch back and forth between those, I've cut off everything below a certain certain reliability in my Hess version. But if I go ahead and show the aggregate, um, I'm getting the same result. What will happen if you run the Hess version with a more detailed table that has a bunch of entries for C to I ratio and delay time is you'll get some more detailed variation in the reliability metrics there. It won't be quite so sort of black and white in terms of whether you've got delay spread or not. Let me jump back to my slides here. And finally, this is another this feature had nothing to do with getting up to date with the TSB88 document and making sure that we matched. This actually came from a customer request. We had a customer who had a mix of simulcast groups in a given network area, but also some multicast or sites that were set to their own channel, especially for use cases like shooting down a beach when you might have a directional antenna and you're kind of just filling in the shadowing along the beach. That type of a site would cause a lot of potential time delay problems. So maybe you want to switch that to a a non-simulcast site and include that. You can actually include within the version 2 studies, you can include a mix of simulcast sites and also other sites that are on another frequency that you'll be able to report their reliability as well. And this includes now secondary group interference. And let me switch to my project here. If you can imagine, I have this same scenario, but uh, maybe I'm right on the edge of the county, and a neighboring network might have a simulcast cell or something operating right on the same piece of spectrum. And if I want to model that interference, and that could be a neighboring network, or by the same token, that could be somebody's indoor BDA repeater system making a bunch of noise and spewing power that could, since it's not coordinated with the simulcast network, it could cause time delay interference. So if I go into my studies and, in this simple case, I've just got my master group with 2 sites. But if I set a group of desired sites and then a secondary group, those secondary group transmitters will be considered part of an uncoordinated network. so that they will just always represent interference. So if I'm going to jump projects here, so I've got one of the same example, but with interference, and you can see this is kind of a worst case scenario. I've put an interferer here at the same power level as my macro sites, and I think what we're looking at here is C to I. So yeah, if we look at the status bar here, down here I'm down at negative 24 or 20 dB C to I ratio compared to the desired sites, which are in my, you know, my desired simulcast group versus my bad guys interferer group. Um, and if we set up our reliability studies, this is my Hess simulcast Monte Carlo reliability, and you can see that where I did have a few little areas, like right in here, I had some areas of potential TDI between the two desired sites. And those are still there. But as I get anywhere near this interfering site, you can see that interference has really blown away my signal to noise ratio. And so this, in this way, I can model the impact of that interference. And if I wanted to make this representative of like maybe an uncoordinated BDA or something like that, I could put that inside a building and or adjust its power level. And of course, I'll get a much smaller area of impact there. Um, but again, the cool thing here is you can model that network, which might be complex. It might have multiple simulcast groups. It might have a few ASR or multicast sites. Uh, and it could have neighboring sources of interference represented all in the same picture. And we can still get one study to show us that sort of end-to-end reliability. Um, so that again, the TSB88 spec doesn't say anything about modeling interference as part of that same Monte Carlo, but we had one of our good LMR customers come to us and say, "Hey, this is a use case that we're having to tackle, and we're having to run a whole bunch of these different studies to show, C to I for our multicast sites, then also reliability on the simulcast." And then also incumbent, interferers or potential interferers. So, by rolling in that second group interference, you really can model it in an end-to-end way and account for all the different parts. Um, so again, those are kind of the main differences. And if you want to know the specific details of how any one of these studies is being run, just refer back to that knowledge base article, and it'll clarify the difference, like which one is using the table and which one not. And um, the other difference I could specify here is that the bounded area coverage study, if I go back into my parameters for the TSB88, this new bounded area coverage study will look at all of these parameters, including that required tile reliability. So if you just want one map that shows here's all the area that meets the criteria, and we're requiring maybe 90% tile reliability and, no greater than a given uh, simulcast delay, etc. You can get that all out of one prediction. Um, so I think that's what I had to say about that. I'll go ahead and move on here. And I wanted to touch again on uplink coverage and or reliability. It's easy to get sort of wrapped up in the simulcast studies, looking at the downlink and the potential for TDI on the downlink. But of course, the uplink or talk inside is usually the weaker link budget and more prone to having fading issues. Um, and we still see sometimes some confusion on how best to set up the propagation model and the study type together. Excuse me one second. So I've got an item here reliability versus coverage. And for some of our users, they've decided, hey, if we're running a percentage reliability study on the downlink, on the talk out, if I'm running my Hess Monte Carlo, maybe I would like to run a reliability study that takes the fading into account in the same way, but on the uplink side. And that's what we've got some studies here. These are under the basic study category. And we've got uplink, percent log normal reliability, percent log normal reliability using voting receivers. And then we've even got a third one now that's the log normal reliability with macro diversity voting. Um, and so macro diversity is, in other words, we're essentially combining the received power from all of the base receivers in the desired group um, to account for sort of IP based. Some solutions I think are calling it macro diversity, but that's sort of a recombining where it's not just choosing the strongest receiver as in a traditional voting receiver, but it's able to on the fly switch between them and have the strongest signal in any moment is my understanding of that macro diversity. And if we want to set up one of these reliability studies from the basic study category, it's important we know where to set up that fading. And if I go into my software here and go to the studies menu, reliability methods, here's where I can set up how I want to do multipath fading and rain fading, or I can just switch on to use a log normal distribution and I can input my 5.6 dB of fading or more. If I'm in a high fading environment, maybe I want this to be more like 7 or 8 dB uh, of standard deviation in that fading. And then if I go and set up one of those uplink log normal reliability studies, I'll be able to see that percent reliability inclusive of signal fading and adjust that fading as needed. And so I wanted to again call this out because one thing that can happen is if we're running percent reliability studies, those studies are meant to account for fading. And if I was to also go in here and let's say I want to make sure my prop model is conservative enough, so I say, okay, I want 90% of time and 90% of location. If I do that, I'm applying fading to the propagation model itself so that the predicted signal levels will always be lower than, what we predict will always be lower than the direct path prediction gives us. And in that case, we could be under accounting for potential interference. So typically, if we are going to use those fading studies, or we're using studies that include fading as part of the study result, then we would set up the propagation model to target the average signal level that we're actually measuring in the field. And so, maybe I have these set at 50% of time and location, and I go out and do some field testing and use test against measurements and adjust my clutter losses, or I just decide to apply some margin. As long as I can get that to where my propagation model, if I just run received power, if that's largely lining up with what I measure in the field, then my fading studies should be accurate if those are taking fading into account. However, if I just set up that propagation model targeting the average signal level in the field and run, say, a coverage plot, well, then I'm not accounting for the potential of fading at all. And maybe my coverage plot with just Anderson 2D at 50/50 might be overly optimistic, especially when we layer in the potential for fading over time and the potential for TDI. So, I've seen new users sort of either not do either or do both and use a prop model that includes fading and then also studies that include fading and say, gee, why are these so pessimistic? And so in uh, whatever the use case is, just keep in mind what studies you're going to run and where in the prediction you want to take fading into account. And you know, uh, two and two equal four, but three plus one also equal four. So in that way, there's more than one perfectly correct, perfectly acceptable way to set this up. Um, Myself, I think it's most consistent to use the uh, Monte Carlo reliability on the downlink and the log normal reliability using whichever kind of voting receivers. Um, on the uplink. I think that's the most consistent, and it allows me to set the propagation model up to just target my field measurement data, and I don't have to do any adjustments for fading right there in the prop model. Um, but bear in mind too, you can have more than one prop model configuration as well if you want to um, use one model for one purpose and another model for another purpose, that's allowable. Um, I think it just kind of introduces confusion. The next item, or maybe frequently asked question about these new delay spread studies, is we've got a few different delay spread study types in the basic study category. So if I go in here to add study, and under basic, I've got a simulcast RMS delay spread, and I've also got a maximum simulcast delay spread. In the case of the maximum, it just finds the worst offender in terms of delay time and just repeats or reports that delay time. Um, Versus in the RMS, it's weighting those delay times based on the relative signal power compared to the desired. And so this is more a representative number of the kind of combined delay spread of all the interferers. And these methods are sort of older methods. In the latest revisions of the TSB 88 document, they recommend calculating the delay spread not based on just the direct difference in path length, which that's what these do is we just take the path length, direct transit distance between them to come up with our delay times. Under the TSB 88 Monte Carlo category, if I were to run this simulcast delay spread Hess, what that Hess method does is to take that direct path delay time difference and double it so that if, let's say there's a potential for multipath, either from big terrain features or from dense urban environment, where you could have a reflected path that has a greater path distance than the just the direct line of sight path. And so in order to be a little more conservative with our delay times, the Hess method takes that transit distance and or the direct path difference and doubles it. I think sort of with the idea that once you've gotten past doubling the delay spread, any longer path than that is going to be so substantially degraded in power as to be, not a problem anymore. Um, I have heard just sort of analogies from a couple different users that these times, the Hess delay times, uh, match more closely what they're finding in the field, especially in highly reflective environments. If there's not a whole lot of foliage to absorb the multipath, we've seen some numbers that are getting close there. Um, so I guess bear that in mind. If you ran the old RMS delay spread or maximum delay spread, you'll see a larger delay time now when you switch to the Hess method, or any of those TSB 88 calculations are also going to use that Hess delay time. Um, Okay, so that's all that I had to say about the TSB88 features. I'm going to take a look at my Zoom console and take a quick look at the Q&A window here. Go ahead and if you want to add something in the Q&A field or raise your hand if you've got any questions, I can try to answer those here. Um, One question is, does this mean that the V2 studies will be better in terms of reliability or sort of more optimistic? And boy, we went round and round internally about whether to call the version 2 study the strict version. In cases where you definitely do have uh, time delay issues where there's a timing problem and the coverage footprints of those two sites overlap fairly strongly, then it'll actually look worse in those those circumstances, or for a lot of the map, it'll look worse because when we're not doing any RMS averaging of the impact of the delay, we're saying this incoming signal with whatever power it has in this moment of fading, if it's outside the allowable delay time, then it gets counted as interference. So for areas where you do have delay spread, you will see a lower reliability typically than you might have seen in the V1 study. However, the flip side of that is that when the oh shoot, I can't get back to my other got to get back to my other project. In the overlap areas here, where I don't have the impact of that interferer up here to the north, and my two desired sites are overlapping so that that delay spread is within the delay window. In these areas, you're going to tend to see a little bit better or more optimistic reliability because now we've got those sites reinforcing each other in a manner of speaking. It just means that if the signal level from my key site, my site A, for example, if that happens to be in a moment of deep fade in one Monte Carlo pass, then chances are the B site will not be in a moment of deep fade, and it effectively its signal level will fill in, and you can have momentary switching back and forth of which one's the strongest, but if there's essentially no time delay between them, it has zero impact on the audio quality. So I can't really say that one study will be more optimistic or more pessimistic than the other. Um, but you will sort of see some differences. And we left the version 1 studies in place because we've gotten feedback from some of our users that these work just fine. And certainly they have already sent these results out to customers, and it's very hard to explain when your prediction changes. Um, all that to say, if you ran a version 1 study and you run it again in the version 2 and things are a little bit different, I don't think it means that, there's some major problem in your network. It may just be kind of an artifact of the difference in calculation method. Um, Another question we have is the Hess V2 using both the table, the signal versus delay table, and the required delay parameter. And in this case, n no, that required delay parameter essentially comes from the table in the case of the Hess study. Another question, what are the typically allowable delay spread for common services like P25 DMR? Um, this is really a function of the equipment and the modulation type used. The TSB88 document itself has a big table. The other variable that it's based on is the uh, the DAQ level, the digital audio quality level that you're targeting. So there's not really one answer here, but you want to look up either from the TSB88 spec what the required simulcast delay times are, Or if you if the manufacturer gives a spec, I would say that overrides the document. And if you have the ability to bench test that equipment on a fading channel simulator in the lab, then you can create your own simulcast signal versus delay file based on real measurements of how that receiver performs under different channel conditions. And I would say that those measurements are superior even to manufacturer or TSP88 recommendations. Um, so there's not one answer, but I would take a look first at the TSP88 recommendation for your DAQ level and product and everything, um, or or the spec sheet for the equipment. And if you can't find it, do feel free to just start a support ticket, and we can try and help you figure out what the right value to use is going to be. Another question, is there a way to quantify RSSI and how much more constructive interference there is with HES version 2? I haven't really considered the second question. Certainly, with any of these studies, you can go in and run receive power at remote studies so that you can just see what's the average predicted signal level from each of these different servers at each grid cell. And that can really help you understand what's happening. Um, the other one that I really like to run is the C to I primary to secondary group TXs if I am including some interference sources in there, because that'll help me sort out interference from TDI, potential TDI interference. Of course, if you run a C to I, a traditional basic group C to I study between two co-channel sites, that will just show interference in the areas that those are both covered, but you won't see that constructive interference where the simulcast delay times interfere. So that could potentially be a helpful way to sort of, if you run the reliability study alongside a C to I study, you can kind of see, or rather, you can disentangle whether drops in reliability are due to a coverage problem or they're due to a potential TDI problem. So hopefully that answers the question to some extent. Like I said, if anybody has any follow-up questions or wants to talk about this in more detail, do feel free to start up a support ticket and we can talk in depth about any of this. Um, Another question referring to the changes in the fading calculation between version 1 and version 2. Um, well, I can say the first and most important one is that in the version 1 of the study, um, either by oversight or by design. I'm not really sure. The original architect of the software, unfortunately, is no longer with us. But it was only fading up and down the desired signal level in each Monte Carlo draw. The potentially interfering signal level was not being faded. And the other piece of that, frankly, was a mathematician thing that I didn't fully understand about how they were generating the distribution of random numbers. Um, and I think effectively one, because the two different distributions weren't being overlaid, that was the greatest problem. But then also the TSB88 spec itself, I think, had a particular or had a recommendation for how to come up with that distribution. So we went ahead and used that. Um, Another question. Oh, the sorting of delay times. So when we are let me go back to my other project here. I'll go back to my simple version. And when we're sorting the incoming secondary or third signals, uh, we in the sorting we're using the difference in delay time value. So we're gonna calculate the time of arrival of, signal one or the strongest signal, and then we're gonna calculate the time of arrival of the second, third, fourth signal. And for each of them, each one of those potentially interfering signals gets its delay spread relative, or the difference between the strongest or desired signal and that potential interferer. So each one of those potential interferers is going to have its own delay time just based on the distance and the Hess method. And as soon as you cross into the allowable simulcast delay area, that's where you'll see that sort of constructive interference, or at least you won't see any degradation in reliability. And as soon as we cross into the area where that delay spread is too great for the interfering signal, it will start to degrade the signal to noise ratio, also called CPC. And so you'll see the reliability failing because the CPC is now too low. Um, I think there's one other question here about the algorithm that we're applying for the voting receiver, uh, standard voting receivers versus macro diversity voting receivers. And I don't have that information and understanding ready at hand. Um, I was under the impression that it takes all of the potential, so the macro diversity voting receivers, I think it looks at the uplink signal power to each one of those receivers, and uh, basically gives us the odds that it will have a an acceptable signal level to one of those base stations at any given time. I don't think that it's doing a Monte Carlo. I think it's actually adding the probability. It's doing figuring out the fading distribution for each of those sites and then adding those probabilities together. I, I'm going to go ahead and say I believe that that is the answer, but I will double check on that, because I don't think that in our macro diversity study. And again, in case you're wondering how to get to that, I would go to add study, and this is in the basic study group, and just write down here the uplink percent log normal reliability with macro diversity voting. I believe this is adding the probabilities together of an acceptable, you know, uh, received signal power, and giving you the probability that one of those base stations is going to be able to receive it at any given moment. I don't know if there's any accounting for the combinatorics or anything there. I don't think that there is. Um, but if there's a deeper question we need to follow up on that, please do send us a note. Um, Okay, so real quick, I know we're coming to the top of the hour. I've just got two more quick slides. Uh, this stuff has not even anything necessarily to do with LMR and DMR. They're just my top three new features from this year that I think may save you time and headache for a bunch of different use cases. One of them, any area study you set up now, if you want to run it for body mounted wearable radio and a vehicle mounted mobile and etc., you can set up the study once and just check which mobile remotes you want to run that for. So I could set up all the different mobile types I want to look at. And when I run that study once, it's going to generate three different layers that I can click on and off for each one of those different mobiles. So you don't have to copy the study 3 or 5 times and rename it for each of your mobiles. You can just check those on now. Next, the Anderson 2D propagation model now, if you want to adjust how much diffraction loss you're getting, either for terrain obstructions or for MCS buildings, if you're using discrete building polygons, you can go in and adjust how much diffraction loss you're getting for either of those kinds of obstructions. And the main use case here is if you've got building polygons for a dense urban area where you've got a lot of reflected paths, you can reduce that building diffraction factor to show that potential for multipath, um, and get a model that'll line up a little better with your urban drive test. So that's people have also asked for this in order to reduce the terrain diffraction in areas that are very arid and steep and have a lot of reflectivity there too. So you can make adjustments there if you need to get better agreement from the prop model with your measurements. And finally, this one might be my favorite. Anytime you set up the color scheme for a study, so if I go into study display style, set signal and color levels, if I've got a nice intricate color map for this type of study, I can just go save color profile and give that a file name, and that gets stored into my project, but I can also open that up from any other project. Any reliability study that I set up, I can just go into that set signal and color levels and hit the import button to bring in that same color profile I always use. And usually I'm sure I've lectured most of you at some point that, hey, if you set up your project template so it has all this stuff ready to go, then you never have to touch it. But let's face it, we don't always have the project template with everything ready to go. So just being able to save and import a color profile for studies, I find to be a huge time saver. Hopefully you will as well. Lastly, we wanted to make an acknowledgement, which is a little bit strange for us at EDX. Um, we'd like to take this opportunity to express our thanks to Bernie Olson and CSI Telecommunications for all of his guidance and feedback that he gave to us over the years before his retirement. Um, his concept for using this measured delay spread curve in order to give us a more detailed simulation of potential interference, that's really the basis for both that TSB88 update, the recommendation update, and also our reliability studies were version one of them were written in, direct sort of back and forth work and feedback from him. So obviously we owe him a huge debt on this, and the concept has proven to work very well. We've had positive feedback from a number of our users who drilled in to use this and reveal areas where they get reports out in the field that say, "Hey, every now and again on this bend in the highway, we can't understand what dispatch is saying anymore." And by using these studies and getting them all tuned up with measurement data, we can reveal some of those problems in reliability. So it's just great to close the circle and see when a simulation works. And we really want to acknowledge Bernie for his contributions to that, and of course CSI Telecommunications as well. That's all I had for you today, and we're at the top of the hour. If you've got additional questions, additional use cases that you need to look at and want to talk to us about, please do either reach out to us either through your sales rep or through support at EDX. Or, of course, you can always go on to edx.com, go into the support portal, and raise a ticket with us, which is probably the fastest way to get a response, whether it's a question or feedback, bug, whatever it may be. Thanks again for taking the time with me today, everyone. I realized I said that would be short, and then I took every last minute we had. So I appreciate you hanging with me, and we'll talk to you again soon.